sir. 6 p.m. now and one.
There was
So dear participant, yeah. This is, so he is a principal CSIR is the Chennai. So his research damage structural component. He also works in international public and he to the we are truly privileged with us today session.
Sir, I'm sorry to interrupt, sir, but the voice is breaking.
Is it to you, sir?
The voice is getting
Sir, your voice.
between.
Sir, your voice is breaking like anything. You couldn't hear anything.
Yeah, Dr. Sushanta, you can close your video. Yeah. And
Yeah.
then,
Am I audible now?
yes, now it is fine.
Okay. Okay, sir. Okay, so we are happy to welcome Dr. Balasubramanian, sir. He's a principal scientist at CSIR-SERC Structural Engineering Research Center, Chennai. So, sir has completed PhD from IIT Madras. So, sir research focus on the seismic behavior and performance assessment of the masonry buildings, damage gradation, condition assessment of industrial building and structural component, etc. Also, sir works on the various field in the structural engineering. And with several national and international publications to his credit, sir has significant contribution to the research and consultancy projects. So we are truly privileged, sir, to have you with us today.
Thank you.
Thank you, sir. You may proceed now. Over to you, sir.
Thank you, Professor, for the kind introduction.
Sir, just small introduction, sir. I want to make one small announcement. So before we start, a small announcement for all the participants. If you have any question or clarification during the talk, please type in the chat box and we'll address them in Q&A session at the end of the talk. Thank you. Thank you. Over to you, sir. Thank you.
Yes. The content sharing is not available to me.
Sir, I'm giving you the access. Is it fine now, sir? Can you share it now?
Oh, okay. Oh, now also it is saying so. No, but you are no presenter. Yes.
It's okay. Yes, sir. Your screen is visible.
Good evening, everyone. Thanking you, Professor Sushanta, for the nice introduction. I'm going to talk a bit on testing of brick masonry specimen from seismic performance perspectives. Despite a very long history of brick masonry in its existence, it is one of the least understood civil engineering material, and as a result of it, not much of the existing structural masonry buildings are engineered. Though some kind of a limited engineering has been in place, most of the buildings are not so. By the way, my talk will be restricting only with respect to the structural brick masonry buildings, or otherwise colloquially referred as load-bearing brick masonry buildings. We are not going to discuss anything on the non-structural infills of the high-rise buildings or any kind of a framing structures. So in this, I'll just, for the benefit of the participants who are not well versed in the engineering of structural brick masonry buildings, I'll just introduce some of the fundamental things so that it will be prudent to discuss further. So in this, in these figures, there are three typical failure cases are present. Okay, one showing the rocking mode of failure or toe crushing mode of failure. The other one is sliding mode of failure, which is on the top
Sir,
left.
excuse me.
Sir,
Slides are not visible.
have you shared? Slides are not visible. Sir.
Oh.
It's not visible, sir. Please make it a full screen. It's not visible.
Yeah.
Yeah.
Yeah, now it is visible.
Yeah. So first I will discuss about the fundamentals so that people, the audience can cope up with the further discussions. So this is these are all typical case of in-plane shear failure. One is the sliding failure, which is on the top left. The next one is flexure, rocking, and toe crushing. There are three different names given to this, depending upon the progress. And then the diagonal tension mode of failure. There are also two subcategories in it. One is diagonal tension failure through bricks or diagonal tension failure along bed and head joints. So in this, closely look at the organs. There is a sill masonry, okay, over which we have this pier systems, and then we have spandrel masonry that is above the lintel, and we'll have a roof. This is a typical thing, but the three terms: the spandrel masonry, which is the portion between lintel and the roof or floor, and the pier masonry, which is between the sill and lintel, and the sill masonry, which is below the sill to the floor. So these terms will be helpful for you to follow. So in this, if you closely look at the capacity equations, the sliding mode of failure, which is nothing but the Moore Coulomb failure criteria kind of thing, where you have some cohesive component, which is the shear bond strength, times the coefficient of friction and the pre-compression load, which comes out of the dead weight of the structure. Okay, so it is more or less, it is something similar to the Moore Coulomb failure criteria. The next one is the diagonal tension failure through bricks. This is nothing but the initiation of diagonal tensional cracks at the center of the pier system, and it starts with the center and then proceeds along the diagonal periphery. So it is like a progressive thing which stems on either direction depending upon the direction of shear force. So as a result, this X type of cracking will form. The another one, the third one, the rocking mode of failure, which some literature will talk call it as a flexure mode of failure. Some literature refer to it as a rocking mode of failure. Some literature refers it as a toe crusher failure. All these are different phases of these components. See, initially, the masonry part or the pier, okay, it will bend like a flexural deep beam, that is the starting, and then the separation of heels happen, and then on either way the separation of heels happen. So as a result, instead of the curvature formation, now the curvature formation will be released, and then as a solid mass it will start rocking, and then beyond a point the toe compression levels will be increasing depending upon the angle, and beyond a point what will happen is the toe will get crushed. So these are different phases in the transition, but some literature give the lower bound, some literature will talk about the middle bound, and some literature will talk about the upper bound, and so they names accordingly. So it is nothing but the third expression, okay. It is similar to the having a compression this thing, and then balancing, okay. The weight will be balanced by a compression toe. The moments, the eccentricity of the center of gravity of the mass and toe will be the resisting. Beyond a point, when toe crushing compression stresses increase, it will start crushing, and then it will fall down. So this is called the rocking mode of failure. So these are expressions that are available in Eurocode, but basic mechanics behind this failure is like what I explained. Okay, so now getting really into the topic, we need some mechanical properties to properly engineer a structure, right? Because on one hand we will have force that's coming. Okay, on the other hand, you will have some resistance capacities. To understand the resistance capacities, we need a determination of the respective strengths, isn't it? So this determination of mechanical properties is important in the case of for seismic analysis. For seismic analysis, the list of important mechanical properties is listed here. Compressive strength of brick masonry. This is not of the brick or mortar separately. This is the compressive strength of the brick masonry. And then elastic modulus of brick masonry, tensile strength of brick masonry, shear bond strength, bed joint friction coefficient, and then coefficient of friction of the brick masonry. And then there is importance to establish the interdependencies between these mechanical properties, because see, in the case of concrete, and concrete would have seen, if the compressive strength of a concrete is known, we can indirectly estimate the shear strength, maximum shear strength capacity. You can get the tensile strength, isn't it? So that is what the interdependencies that we are talking about. These are the things that we need to understand, and also we need to establish interdependencies between between the mechanical properties of physical constituents of brick masonry. In brick masonry, as we all know, there are two physical constituents. One is the brick, which is otherwise called as the masonry unit, and bed and head joints, mortar joints. Okay, these are the two physical constituents. While I'm saying there are two physical constituents, it is inherently understandable that there is something called physical constituent or virtual constituent, which is nothing but the interface between the bed joint, mortar joint and the brick. That means if there is a brick, above that there is a joint and then there is a brick. So there are two interfaces, okay, between this mortar joint and the brick above and mortar joint below the brick above. So that is construed as a non-physical constituent, because as the characteristics of the masonry not only depends on the physical physical constituents, but also depending upon the nature of the interface, depending upon the smoothness or roughness, depending upon the presence of rock. All that matters in the case of brick masonry specimen. Brick masonry specimen, I mean brick, mortar put together as in a periodic fashion. So this is what masonry is all about, and to determine the mechanical properties of this masonry, we need specimen. Like the case of concrete, what we will do, we will make the concrete material, which is again a mixture of different physical constituents, and then molding it to specific shape that may not be of the there are some typical specimen sizes, shapes and sizes suiting the different mechanical properties, right? We use either concrete or cylinder for compressive strength. For split tension, we use cylinder specimen, and for getting this flexural bond strength, we use prisms, right? They are not as you see, to design a structure, we use these material properties and then map to the map to the capacity of the structural elements, right? We don't test the structural element sized specimens directly. These are all representative samples, specimens, right? Cubes, cylinders, and prisms. Similarly, brick masonry also, for testing the capacity, the mechanical properties, we have to have some kind of a brick masonry specimens. And to for experimental investigations that, and to characterize different brick masonry used in different parts of the country. See, for India, we are having multiple regions. Having multiple regions with different kind of brick material, brick availability, depending upon their chemical and mineralogical characters. The strengths are varying significantly. So, for instance, if you look at the intergagetic region, the compressive strengths, even in the table molded ones, will be like something around 16 to 20 megapascal. When you look at the Deccan Plateau region or peninsular India, it will not be. It will be somewhere around 4 or 5 megapascals. So to achieve higher strengths, people go for compressed molding kind of things. Improved manufacturing techniques. So in order to understand the brick masonry and the physical, understand the interdependence between the physical constituents and the brick masonry, we need a lot of experimental data, right? Based on that, only we can correlate and then come out with models to understand the real characteristics of brick masonry, engineering characteristics of brick masonry from the mechanical properties of the specimen as well as from that of the physical constituents, isn't it? So to characterize this, we need a good amount of data is required, but do we have really common accepted testing procedures in our country at present? The answer is no. We do not have standard test procedures for testing brick masonry. Whilst some international standard talk about Eurocode, Australian code, ASTM have these comprehensive test procedures for different mechanical properties. We do not have as of now. And then, so, you know, we took up a study of getting the comprehensive test procedures for evaluating the brick masonry specimens. And this is what is going to be the part of the top. This was going to be the top. Okay. So I was talking about test on physical constituents, right? One is test on bricks and test on mortar, and then test on masonry. So for test on bricks, we have standard test procedures. For test on mortar, masonry mortar, we do not have comprehensive test procedure. So compressive stress and behavior of compressive strength of bricks, water absorption of bricks, and also initial rate absorption of bricks. For all these, we have procedures. The initial absorption ratio, initial ratio of absorption may be found to be significant, sensitive to some, according to some studies, and some studies talk about water absorption itself is enough, no need for IRE and all. So anyway, that is a different thing. But what we have is the compressive strength of bricks, water absorption, and IRE are there similarly. But for mortar, which is the second physical constituent, we do not have compressive stress strain behavior procedure, and we also do not have test on masonry, compressive stress strain behavior, flexural bond strength, shear bond strength, and then shear strength. Here it has two components: shear bond strength and coefficient of bed joint friction. Like in the first slide I told you, there are two components: coefficient of friction and then shear bond strength. So, and then the split tensile strength. Compressive stress and behavior is required to get the toe crushing failures capacity. Flexural bond strength is required for out of plane flexural resistance, anyway, which we have not discussed about. And then for shear strength, for both for sliding shear resistance as well as diagonal tension along bedded end joints. This is also more or less like a more Coulomb failure kind of a thing. And then split tensile strength, which is required for determining the capacities for against this diagonal tension mode of failure through bricks. I may be going a little slow because considering the vast heterogeneous audience, for some people it may be a little boring, but in order to cater to the nature of the heterogeneous audience, I'm going a little slower here. Then, as a result, we just made a survey of literature and standards that are talking about the different tests on the physical constituents as well as the brick masonry as such, as a material. Okay. We have identified some standards and also some literature pertaining to India, because that kind of an experience will also lead us to a good understanding of the procedure, right? Because here we are not going to talk about experimental analysis. We are going to talk about how to do the experiment, what is the procedure to be followed, and what is the nuances behind each and every step that we are going to adopt, we will have to adopt. That is what is going to be covered in my lecture. So what are the salient aspects of the comprehensive test procedure? If you look at, there are 9 comprehensive salient aspects. Conditioning of brick units, mixing of mortar, type of specimen, number of specimen, fabrication of specimen, capping of load surfaces, and then cleaning of specimen, requirements of test equipments and machines, and rate of loading. So amongst these, some of the aspects are common to all the mechanical properties that we have discussed. Say, for instance, conditioning of brick units, it is common in whether it is compressive stress and behavior test or shear strength test or flexure test. It is going to be there, isn't it? Similarly, mixing of mortar, there are some common aspects and then specific aspects that first we will talk about all the common aspect ones, all those common ones, and then we will discuss about the specific aspects. Okay, this slide has come now. Conditioning of brick units. Is it visible?
Yes, sir. Yes, sir.
Yes,
Slide
sir.
is visible.
Because in my another phone, I also logged in. I was seeing it was rolling. Okay. So conditioning of brick units is, though it seems simple to understand the, if you can understand the masonry's interface, brick mortar interface, in a better sense, it can come out with producing good masonry. See, some studies have indicated that there are two stages of hydration that is happening. One is water flow, and another one is reversal of water flow. That is, in the at the time of laying, okay, immediately during construction, we are laying bricks and then laying mortar and then another layer of bricks, isn't it? So initially, water content will be there in the mortar, which will flow to the brick, isn't it? So that is called water flow. Okay, whereby it will deposit the cementitious products along the roughness of the bricks, isn't it? So, by means of that, it will form a good brick mortar interface. Water will take the cementitious part and deposit along the rough surface of the brick. So this is called water flow. The next stage is, once due to hydration, what will happen? Water level in the bed joint mortar will continue to reduce. Once the water content in the mortar get reduced due to the hydration, okay, the reversal will happen. So both stages will be there. First stage is called effect of water flow, and then reversal of water flow. So one of the earlier studies by group that's SESDRRBI, this effect of water flow on the composition and hydration conditions of the brick mortar interface have to be taken into account to explain the bond strength development. So it is one of the important aspects in the formation of the very good bond, isn't it? So there are studies which correlates initial rate of absorption versus bond strength, and then there are good amount of these things on the compressive strength of mortar, the effect of compressive strength of mortar on the bond strength. So based on more and more understanding, we will come to a conclusion on this. However, what needs to be understood is that, so to facilitate this effect of to facilitate this flow of water from mortar to brick, and then the flow of water from brick to mortar, in order that to happen, our bricks should not be fully dry. See, if bricks are fully dry, because of the presence of air, the flow will be getting obstructed, right? So we shouldn't use fully dry bricks. So to at the same time, we shouldn't use saturated brick also, isn't it? If we use saturated brick, what will happen? The already water will be present in the cavities. That is, neither dry nor saturated ones are preferable for the water flow to be happening effectively. So a partial saturation is important. That is why we always use this, saturation, pre-wetting. Some studies have indicated that 70% of saturation level is seemingly reasonable, which is also understand from the heuristics, it is quite reasonable, I would say. So we have to have a partial saturation mechanism suiting this requirement. What we have to do is we have to perform saturation levels for different duration of soaking, maybe, and then depending upon that, what we can do is we can decide to what is the better duration for the specific type of brick that we are going to use in our study. Okay. Next is the mixing of mortar. There are two important things. One is workability of the fresh mortar and also maintenance of the same rheology during the entire fabrication, isn't it? So we have to have a reasonable workability and also the kind of the little bit, pasty flowing consistency is required. That depends on different types of sand, harshness and the fineness of sand. All that has to be taken into consideration. So what is the method to define, determine the workability is mortar flow test or cone penetration test or slump value test. So mortar flow is the best suitable for this case because it is simple test and also quite sensitively determines the workability in respect of the masonry mortar. Okay, so can carry out this mortar flow test. If it's not available, then we'll have to resort to slump test itself. So far we do not have the proper limits to proper limits to define what is the range of workability that we have to maintain. But we, in due course of time, after a vast study on this assessment, we will have to come to the level. But at present, we are in the stage of standardizing the procedure, isn't it? Okay. So as I said, the slump test is simple, but mortar flow is more sensitive and better suitable in my opinion. And also, I was talking about the second point, which is freshness or maintaining the rheology over the time of during the time of fabrication. For fabricating the specimens, we're using mortar. Initially, it may have some rheology. After some time, the quality changes, isn't it? So what we have to do is we have to mix the mortar as a dry mixes, have small portion of dry mortar, and then water required have to be ascertained for the specific case. Okay, and then the requisite amount of water has to be added in a single stroke. And then use the mortar for say within half an hour or so. So supposing if you are using some kind of about 5 or 6 kgs or 10 kgs, it should be fine enough for fabricating specimens. Within that half an hour, we can consume. So beyond that, we shouldn't use. You have to throw away that mix, and then fresh mortar has to be prepared. And then number of specimens. Number of specimens in the case of concrete, for some parameters, you would have used some 3 or so. For some parameters, they will resort to 5 specimens, isn't it? All that, the number actually, it's depending upon the scatter. The epistemic uncertainty associated with the with the parameter that we are discussing. If the scatter is more, to have a confident estimate, naturally we need more number of specimens, isn't it? So at the same time, we cannot have a very high number of specimens for getting higher confident estimates, because we need to strike a balance between the bias of the test statistics as well as cost involved. So as a result, we can have an optimal strength, number of specimens required for each and every mechanical property that we have to determine. We have done some works on this. We'll discuss about this in detail while we are getting into that part. And then for characteristic mechanical properties, as we all know, we will not have a negative tail, isn't it? So often people use log normal distribution for characterizing material properties. So based on this, what we have done is we carried out a vast survey of literature reporting different number of specimens and number of the scatter coefficient of variation that they have reported for different tests. So what we have done is we have fitted a log normal distribution, and then based on that we computed the generalized p-value, and we have carried out this standard student t-test. As a result, what we have identified, with increase in specimen, in the number of with increase in scatter, there was an increase in the there was a significant reduction in the length of confident estimates, and so at the corollary side, we increased the number of samples. Okay, so for the case of sample size of 5, we fitted for different cases. Here we are talking about the values, the length of confidence intervals that are reported are pertaining to different studies where they have reported this average value and COV in some instance, or some in some instances they may not have reported. We computed. Okay, for a sample size of 5, we obtained the length of confidence interval between like 12.91 to 100, and then for sample size of 10, it was between 7.44 to 58.08, which is drastically reduced, right? Similarly, at for a sample size of 15, the confidence length of confidence interval further is drastically reduced to 5.75 to 44.97, and beyond that, if you see, not much of a significant reduction. It was simply reducing to 4.86% to 38%. So that was the bound. Okay, so beyond 15, it wasn't coming up. So beyond with the increase in the sample size, the confidence interval was reducing, and beyond that, it was not reducing much. And then at the 15 number of samples was found to be reasonable in our study. Okay, and then The next is fabrication of specimen. In the case of concrete, we use the word called casting, because casting, we have a mold, we have a semi-plasticaceous liquid kind of a thing, okay, gel kind of a thing, concrete, that we will pack it in in the volume of the mold, and then after drying or after hardening, we remove the mold, isn't it? But in the case of brick masonry specimens, we have to use the term called fabrication, because we are using some brick, mortar that are arranged in some periodic fashion. Kindly excuse me, just a minute. Sorry for the interruption. Okay, now we need to fabricate the specimen, and for the purpose we need to use alignment jigs, plumb bob, spirit level, etc. And we have to conform the desired geometry of the specimen. See, for instance, for the case of verticality, at least along two adjacent faces, one header face and structure face. At least we have to check that, because there will be small variations in the width and length, isn't it? So, and then we need to confirm the top face of each brick shall be horizontal. Okay, and then to make sure that the brick units have to be placed in such a way that the frog should be facing upwards. That's how in normal practice people use, right? Because when we are facing the frog upwards, the mortar gets filled. If you are facing the frog downwards, we see the mortar may not sneak through the frog, isn't it? And then we have to maintain the thickness of the mortar joints uniformly. There will be multiple joints, brick mortar joints, okay, and then the uniformity has to be maintained. So these are all the conditions that we have to ensure for fabricating fabricating a good specimen. And then capping of loading surfaces. Either cement mortar or sulfur is being used for concrete specimens, but in the case of brick masonry specimens, capping has to be done with mortar which is much richer than the bed joint mortar that we are going to use in the study. And the thickness of the capping also should be kept as minimal as possible, just enough to fill the undulations. That's what the condition is. And then next is a curing of specimen, because the curing plays an important role in attaining the hydration of the mortar, as well as the formation of good brick mortar interface. Not only workability, curing also plays an important role in the formation of this brick mortar, quality brick mortar interface. There are many methods for normal curing of brick masonry. So, for instance, British and Australian standards, they simply cover the specimen with moist, tight bags, and they keep them undisturbed. American standards also, they keep the specimens with mortar type bags, but they place in a temperature controlled humidity chambers. But considering the hot weather conditions in most part of India, such dry methods may not be suitable. So what we have to do is we will have to either go for either wetting the specimen using gunny bags or submerging under water. In the initial stages, say for first week or so, the water has to be, the watering has to be done in a much faster interval, much closer intervals, so that the mortar gets hydrated properly in the initial phase, and beyond that the hydration rate will be higher. That's what the reason I am talking about. So beyond 7 or 8 days, the hydration rate will be low, and then we can reduce the watering, or alternatively for first few days we can keep the specimen soaked under water, and then beyond that we can place the specimen covered with moist gunny bags. But supposing we are using the soaking underwater method, we will have to place some 2 bricks on the top of these 2 bricks. That is like to have some kind of a minimal, some compressive stresses, minimal compressive this thing, so that the soaking doesn't separate the specimens. In some cases, if we are keeping the specimen under water for a long time, the water without any kind of this kind of a pre-compression, minimal stresses, separations have happened in our this thing. So what British standards 5628 was giving was like somewhat around 0.05 megapascal compressive stress has to be there. That is what it says. But equating that to that level, we can place 2 bricks over this specimen at the time of curing. Now, see, all these aspects so far we have discussed are common aspects. Now we are getting into the specific aspects. The compressive stress-strain behavior of masonry. For this, there are different specimens used in the literature. One is stack bonded prism, and the other one is wallets. And then for stack bond, I'll just go to that. Yeah, okay. Stack bond prism figure I will show you later. Okay, and then wallets. Stack bonded prisms are suggested in ASTM. Pragma, the wallets are suggested in British standards, and then from the Indian standard 1905 also for determining compressive strength. So here we are talking about compressive stress strain behavior, that is strain stress ratio relation. Entire stress strain curve we have to plot, isn't it? Because that is required to determine the elastic modulus. The 1905 present code suggests this stack bond prism. Stack bond prism means we are laying 1 brick above the other with the mortar in between. So 5 brick stack bond prism means 5 bricks will be there. In between there will be 4 mortar interfaces, and then top and bottom faces will be very high rich mortar capping. Okay, the aspect ratio is nothing but the least lateral dimension, height to least lateral dimension ratio, which is 2 to 5. That is what the code suggests. So we also felt that stack bonded prism are generic ones, whereas in the case of wallets, to construct a wallet, to fabricate wallet, we will adopt some bond patterns, right? Like English bond or Flemish bond or different types of bond. So the test results also will be applicable to the specific type of bond. So in order to have a generic specimen, better we go for this stack bond prism. For compressive stress strain behavior of water, for compressive stress alone means we can use cube specimens, but as I told, we need compressive stress strain behavior so that we can get the elastic modulus of mortar also. Elastic modulus of bricks are required, elastic modulus of mortar is required, so that when we are characterizing the masonry as a material, we will be either using mathematical homogenization or any other technique. So for those things, we need this elastic modulus of both physical constituents, isn't it? So for that purpose, we need compressive stress strain behavior. So this compressive for mortar, we have to get the compressive stress strain relation. Okay. We will for getting the compressive stress strain relation, we can use a cylindrical specimen of say 150 mm diameter and 305 mm height specimen, or we may either even use 100 mm diameter and 150 mm height specimens can be used. So this is the stack bond prisms I was talking about. On the left one, A, there are 5 bricks with the 4 mortar joints in between. So this is the stack bond prism, and this is the valid specimen. This is a English bond valid, and this is a next one is a Flemish bond valid. So this is running bond valid. Another one is English bond valid. Okay, so when we are testing the specimen, the results of the masonry will be specific to the respective bond pattern. But this stack bond prism is a generic specimen. And then type of specimen for performing the flexural bond strength of masonry. For determining the flexural bond strength of masonry, have either prisms have been used or wallets have been used in the past. Sorry for the inconvenience. One more minute. Yeah. Either prisms or wallets can be used in the case of bond strength also, and depending upon the application of mode, there are different ways. One, either a bond wrench test or 2-point bending test can be adopted. I'll show you typical things. Yeah. So the first one, first A and B are the test on valid specimen. Then C is the bond wrench test and D is the beam test. So here, in the case of valid test, there are 2 important mechanical properties that can be determined. One is flexure of masonry along bed joints and flexure of masonry along normal to the bed joints. So in the case of A, it is parallel to bed joint or along the bed joint. In the case of B is perpendicular to the bed joint. So the KCI is required for out of plane bending of shorter walls, means that it will bend in the horizontal plane. In the case of B, for shorter, the walls with lesser height and longer geometry. Okay, so those walls will be bending in the vertical direction. As such, as thus this flexural bond strength along bed joints is required. In the case of masonry with that are lengthwise smaller but relatively taller in height, in those cases the bending will be happening along a vertical plane, and then this bending flexural bond strength perpendicular to the normal bed joint, normal to the bed joint is required. So in the case of valid specimen, we can determine both the cases, but in some places people always people have gone for straightaway gone for only bed joints alone, in like either using the case C or D, that is the bond range test or 2-point bending test, because in most cases the bending about vertical plane is not predominantly happening scenario, and so the efforts have mostly focused on the bed joints parallel to the flexural bond strength parallel to the bed joint is predominantly focused in the literature. So this is what the case of the shear strength of flexural bond strength of masonry. The next case is the shear strength of masonry. For that, there are standard couplets, standard triplets, and triplets with a cap. I'll just take you to the figures here. Yeah, the couplets, the A specimen here, there means 2 bricks will be there with a bed joint mortar. And then standard triplets is 3 bricks with the 2 bed joint mortars in between. And this is the triplet with a cap in between. And this is a staggered triplet. There are advantages and disadvantages to all these specimens. What we will do is this arrow mark, uniformly distributed vertical ones. There is nothing but the level of pre-compression, because as you all know, in the case of more proliferate area, there are 2 loads. Two loads. One is vertical pre-compression and lateral load, isn't it? If you remember that expression, there will be shear bond strength plus friction bond coefficient of friction times the normal pre-compressive load, pre-compressive stress, right? So from those values only we can construct the more pole failure envelope, and from that we can get the shear bond strength as well as the coefficient of friction. Shear bond strength will be nothing but the y-intercept of the more pole failure area, and coefficient of friction will be nothing but the slope of the more coulombs failure envelope. So different levels of pre-compressions, say 3 or 4 level of pre-compressions can be given and obtained the shear capacity in the lateral direction. To get the 2 or 3 levels of pre-compression, we can perform the test and get the shear strength values, and we can construct the failure envelope. Okay, from that we can indirectly get the shear bond strength as well as the coefficient of friction. Next one is the compressive strength behavior of for requirement of testing equipments and machines. So far we are talking about different types of specimens. Now we are talking about the different testing equipment requirements. See, in the case of compressive stress strain behavior of mortar, you all know for concrete we are having this compressor meter, right? Similar compressor meters are required the compressor, the reason for having compressor meter is to reduce the sensitiveness to the localized temperatures, isn't it? So, similarly, what is the requirement is the range of the strain gauge what we are using should be at least sensitive enough to the say 2% of the expected maximum load range, isn't it? And then for carrying out the test, we have to use the displacement control type of machines with the precision level of at least some 2% of the expected peak load. So this is the criteria that we have to ensure for carrying out this test. And then for compressive stress and behavior of masonry. Apart from that case of mortar, additionally we have to have two important aspects that we have to consider. We have to have a gauge length, and then see, in the case of mortar, I can have different gauge lengths, isn't it? But in the case of masonry specimens, the gauge length should be in terms of multiples of representative volume element in order to totally reflect the volume of masonry and the volume of the gauge. The portion of masonry within the gauge has to be in representative of the periodicity of fabrication. In see the case of yeah, have a look at this diagram. See, in the case of brick masonry, we have brick and then there is a joint and then another brick, isn't it? So look at the right figure. We have a half thick of the bed joint, and then there is a brick and half thick bed joint below. So this is one representative volume element, because see, if we repeat this representative volume element periodically one above the other, the specimen the specimen will be, we can obtain this specimen, right? This is what the periodicity element, that is the representative volume element. So the gauge length has to be decided based on the height of the representative volume element, and then it should be in multiples. Okay, so based on unlike the, because here the representative volume element size and the specimen sizes are more or less not much differentiate. Means that in the case of mortar, the sand particle sizes are much smaller compared to the volume of the specimen, isn't it? But in the case of masonry, the volume of the specimen is significant. Okay, so because of that, we are restricting this this criteria, or height of the gauge length should be in terms of multiples of representative volume elements. I'm seeing the chat messages frequently, which is again disturbing in between. Let us have the discussion at the end of the lecture. Please note down your comments, and then at the end we can discuss. Sorry, today I'm a little busy, so I'm getting interrupted. Sorry for the inconvenience. Yeah, so for concrete, we are having compressometer, right? Similarly, we have proposed this compressometer for brick masonry specimens, brick masonry prism specimens. We have to have rectangular shaped ones that are so that the planes of the compressometer and the planes of the prism are parallel, and we have to have more number of LVDTs across its periphery to cater to the both compressive and also overtraining if any. In this, typically I have shown LVDT is fit, I mean this compression meter is showing two LVDTs, but it will be required I mean at least 4 or 5 LVDTs or strain measuring, any other strain measuring equipment have to be adopted. Which for that, at least minimum of 4 or 5, 4 or 6 in even numbers. Okay, 2 is not sufficient. Either we have to go for 4 or 6 strain gauge, strain measuring units, strain gauge measuring equipment have to be used. And then for testing requirements of flexural bond strength, we can carry out this for carrying out this beam test. We can use these compression testing machine, but the pressure of the testing machine has to be in the range of maximum of I mean at least say 2% of the expected peak load. For shear strength of masonry, the case is different because this is a complex loading arrangement. One is the vertical pre-compression, another one is lateral load. In the figure we have seen, right? To simulate that condition, people have used servo-controlled actuators. So this is a case of a stone masonry specimen where servo-controlled actuator has been used on a vertical and horizontal direction. The vertical one is used for controlling the pre-compression, and the lateral one will be applying the shear force in the monotonically increasing fashion, and from that you will get the shear capacity. There are studies which are showing some kind of a reaction jig like what I shown here. Some reaction jigs have been used to constrain the triplet specimens, and by tightening the screws, I mean nuts, the pre-compression is applied, and then after turning the specimen by 90 degree, we can apply the load on the lateral side. Aligning in the vertical direction using compression testing machine itself. But this type of setup may be suitable in the case of brick masonry, bricks that are very strong and stiff compared to that of mortar. In the case of bricks that are relatively stronger and stiffer, the effect of dilatation will be smaller because volume of the brick in the specimen is higher compared to that of the mortar, isn't it? So if the mortar dilates, it's not a problem. But if the brick dilates, the quantum of dilation will be significant, isn't it? But in the case of bricks being much significantly weaker and flexible compared to that of mortar, the bricks will be subjected to in compression, and then as a result, the dilatation will be significant. So, which is the case in the case of masonry in the developing countries. In developing countries, the compressive strength of the bricks will be much lower compared to that of the mortar. Except in India itself, the Indo-Gangetic region, the brick strength will be much higher compared to the rest of India, isn't it? So, when we are studying this brick masonry that are used in the Indo-Gangetic region, this setup may be helpful. But for other brick masonry that are prevalent across the country, the dilatation will be significant. Means that when we are applying the lateral load, the specimen will expand laterally as a result, but they are restrained already as a result, there will be significant increase in the pre-compression. So to get the constant level of pre-compression, we need to control the load either using the first case, as I showed, servo control actuator, or we can use simple gravity for the load, because gravity, see, if the load is applied by gravity, the dilatation will be allowed. If the specimen dilates, voluminously it will increase, and the weights will go to the new position. And unlike the case of restraint, okay, the weights, if we are applying pre-compression by weight, the weight is going to be same throughout the time duration of the lateral loading. Okay. Next, I will show some figures of testing that will throw more light on that. Okay, and then there is, for rate of loading, normally there are two ways of compressive stresses. One is the capacity determination, the other one is stress strain relation. For capacity determination, somewhere around at a faster pace, we need to carry out the test and get the maximum value allowed. For stress strain relation, we need to do the test in a relatively slower fashion, so that neither creep effects will be reflecting, nor we will miss the post-peak behavior. I mean, the post-peak behavior we shouldn't miss, right? So we have to strike a balance between these two cases, and then we have to determine the stress, I mean strain rate. Okay. So far we have discussed how to do this thing procedure, and then using the devised procedure, we have carried out some tests in our lab. I will just go through that so that we can throw light on it. So for getting dimension tolerance, method adopted in Indian standard is by providing 20 specimens along the length, or along the width, or along the height, that depends, and then getting the overall length. But to suppose if we need the scatter of the dimension tolerance, we need to have the values measured like this, because to ascertain whether how much sensitive these dimension variations are, right? Because we are not just restricting to obtaining the strengths, we are also will be keen later on to map these mechanical properties of masonry with that of the physical mechanical properties of bricks and mortar, right? So for that purpose, yeah, then this is the water absorption test, and this is compression strength test. Here we have carried out flow test we have carried out separately, but I have shown only the slump test. Okay, so for varied water content, we have obtained that slump. Somewhere around say 0.85 or so, it was coming better. So this is preparation of mortar specimens for compression stress strain behavior, experimental setup. Here also you can see this columnar kind of failure. That is by initially near the edges these shear cracks form, and then spall out. The spalling will happen. This is the standard brick masonry prism. How to fabricate, right? I showed you at every level the horizontalness has to be ensured. So this is the first stage of curing that we carried out, and then the second phase after 1 week We used gunny bags for curing. And this is the compressive stress strain relation for masonry test. Sprig, the standard prisms were subjected to monotonically increasing displacement. We used a displacement control machine, and then we obtained the stress strain relation. This is the flexural bond strength test with by carrying out this 4-point bending, and this is the staggered triplet that I talked about for determining the shear strength test. Yeah, here you can see the test setup. So what we do is, I was talking about this dilatation effect, right? So what we'll do is, we'll apply some, use some discs for obtaining, so to apply the load, okay? So, and then the specimen will be kept here. While applying load, we use the second order lever to magnify the effect of the load, okay? So to have a 1 ton load, say we need not have to load 1 ton quantity of disc weight. We can reduce the weight required at the hanger point, which is, I mean, here we have this lever arm ratio, right? So depending upon the lever arm ratio, we can determine the material. So alternatively, we can place some discs and then use the load cell to measure the pre-compression applied here. Okay, we can increase the number of discs so that we can come closer to the range that we are soliciting, and then we can place the brick triplet specimen like this, apply the load and place the discs, and then laterally apply the lateral loads, okay, on the middle face alone, okay. So whereby when the dilatation happens, this triplets will expand. It will not be, there will not be increase in the pre-compression as in the case of the reaction based jigs, okay. Yeah, this is, next one is a split tension test. This is relatively new kind of a test. People have been using diagonal tension on wallet specimens, okay. So this is an alternate to that. So here we fabricated the couplet specimens, and then we extracted core of bed joint in between, and then trimmed those cores. So this is what extracting of core, the left figure A. Figure B is the extracted core, which is of which is longer one, and then we trim the ends so that the aspect ratio of 2, that is length of the specimen to diameter of the specimen is 2. So to that level we can trim and then carry out this split tension test using the compression testing machine with the inclined bed joint, because we are talking about diagonal tension, right? So diagonal tension failure actually depends upon the direction. As I told you, it will initiate in the middle and extends to the periphery, right? So the crack lines will be inclined to the crack lines. The diagonal tension crack line will be inclined to the bed joint, right? So accordingly, depending upon the pier's length to height ratio, or this thing, we can determine the angle of the bed joint and then carry out. Typically, we can use, or generically we can use a 45-degree angle bed joint and carry out the test. Based on that, we can obtain the split tensile strength, and then split tensile strength for the 45-degree angle, and then beyond that, supposing if there is any requirement for change for different angle, We have to theoretically compare. This can be obtained later on based on homogenization techniques we can perform and then correlate the angle sensitivity later on using expressions. But for at the time being, we need some standard values, right? So this is what we proposed. And then these are all the results of those tests. Yeah. So I'll just explain how to interpret also. So here, this is the stress strain relation curve, absolute stress strain relation curve of some mortar joint, mortar specimens. Okay. Yeah, this is the absolute stress strain relation of the masonry specimen. We used something around somewhere around 15 specimens. We carried out the test at 0.003 per minute, that is 0.5 mm per minute displacement rate. Strain rate is 0.003 per minute. So by adopting this for 15 specimen, we obtained this stress strain relation. This is absolute scale, and then we normalized that. See, with respect to the peak load and the strain corresponding to the peak load, the same that scattered curve, we normalized them to this fashion. Now one can easily understand how to characterize, right? So this is by this means of normalizing with respect to the peak load and the corresponding strain corresponding to the peak, we can get the normalized strain curve and typically characterize this strain relation. Yeah, and then normalized strain relation. From that, we compared with the different proposed stress strain relation, and we made some studies, statistical studies on that. Okay. So this is all about I was trying to tell you about on stress now determining mechanical properties. Yeah, this is the shear strength results. See, we carried out this shear strength test with 3 levels of pre-compression, like here. Okay, 1, 2, and 3, and then we obtained this failure envelope, this black line, no? And the intercept we can obtain. The intercept is nothing but the shear bond strength, and the slope is nothing but the bed joint friction coefficient. The 0.03 is the shear bond strength and 0.75 is the typically estimated one. But when we are testing some larger specimens, the shear bond flexural coefficient of friction will come down. In the case of triplet specimen, this is typical range. Supposing if you are testing wallet specimen, the values will be different. Okay. So we have covered. So if there are any questions, you can, if time permits, you can entertain 1 or 2 questions.
Sir, we have got a few questions in the chat box.
Yes.
Shall I ask you? Yeah. So one of the participants asked like 75% of breath saturation will be ensured by inserting it in water for a period less than 24 hours or any other way. Means what is the exact measure of 75%
Sir,
saturation?
what we can do is, see, we will have the water absorption ratio determined. Okay, and then we can soak for 5 minutes, 10 minutes, 15 minutes and weigh, right? So from the 24-hour saturated value, what is the time required for getting this 75%? So typically it may be say 5 minutes or 10 minutes or so. It will come, except in the case of compression, compressed molding, where the water absorption will be lesser. It may take say 15 or 20 minutes, but normal typical table mold ones, in 5 minutes itself that 75% will come. And also we have to keep in mind that when we are taking out, we will immediately not place in the specimen. We will allow some kind of a rest beef while carrying and keeping one handling the previous brick, isn't it? So we have to keep that timing with that kind of a pinch of salt and understanding. 70% is typical range. Okay. Yes, yes. But different bricks will have different porosity, and accordingly we can determine the timing. That is what I'm trying to say.
Okay, sir. And next question is, sir, what is the effect of thickness of brick wall on test results?
Effect of thickness of brick. Yes, it is important because, as I told you, in a representative volume. Okay. Now you look in a mathematical sense. We have a half thick brick bed joint, and then one brick. On a half thick, bed joint the below. So this is the representative volume. Depending upon the thickness, the height of the brick and this the height of this, thickness on either sides of the brick, the volume of the brick to total volume or volume of mortar to total volume changes, isn't it? So in the composite, when the volume of the constituent changes, naturally the strength and performance changes, right? Understandably, right? That is what we are. That's what we are saying. How to maintain the uniformity across the total thing. Okay, we are not saying that you use this as this is the limit or that by numbers, but whatever it is used, it has to be adopted throughout the entire construction, and for that purpose also, when we are studying the test specimen. Across different bed joints, the height of the thickness of the bed joint has to be uniform. So that for each and every case, depending upon the ratios of the compressive strengths of the brick and mortar, later on we may come out with optimal thickness for specific type of physical constituents. They may say some 5 mm to 15 mm. They may be changing because we need to. So to go to that level, we need to understand the behavior of masonry, constituent behavior, this interrelationship, and then homogenization we have to do, and then understand the things in a better way, and then we have to perform this parametric studies for specific cases, and then based on that only we can come out. At this point of time, we are not equipped that level. We are at the moment we are in the stage of finalizing some procedure and then pushing it in code, and then we have to carry out different across India. There are different institutes in their respective regions. They can perform tests, and those tests, if they can be determined disseminated, then later on we can try to establish interdependencies between the brick, mortar, masonry. Okay,
sir.
So that
Is
that's a lot.
FEA volume element.
Sir, now it is interrupting. Now I think again, please switch off your video so that you. Yes, sir.
Yeah, sir, in the modeling of representative volume element in FEA, which nonlinear constitutive relationship are considered? So one of the participants asked.
Yes, that is what, see, I was talking about, using of stack bond prism as a generic specimen, isn't it? Reason is that, see, we are talking about, establishing interdependencies between the constituent and masonry. So when we are talking about masonry, we need to talk about some kind of a generic masonry, means that acceptable generic one. Okay. So the other ones, suppose if we are going for valid specimens, we have to adopt a specific bond pattern, right? Either English or Flemish or any other running bond, whatever it is, we have to adopt that particular bond. So whatever the results that we are obtaining, experimentally determining, that will be applicable only to the respective bond pattern. If you are using same materials, same combination of materials, using two different specimens or two different sets of specimens, one adopting Flemish bond, one adopting English bond, the result may be different. But we have to come to a common generic one. So for that purpose, we use this stack bond prism. Okay, coming to the next one.
Yeah, okay, sir.
Specific
Sir,
point on that homogenization. Now, after getting this, when we are after getting this value, if you are determining experimentally, we will have the homogenized value. When we are using mathematical modeling of the different constituents, brick and mortar, and run numerical analysis, also we'll have the composite behavior. That is nothing but the homogenized one. And we are comparing this, we will come up to the mapping or interdependency, right? Mapping of interdependency, right? For different volume element, we can generate later on. Okay, for different volume element, because for English bond, the representative volume element will be different. For Flemish bond, representative volume element will be different, because representative volume element is nothing but if we are repeating this representative volume element one after the another periodically, we have to get the entire shape, isn't it? Entire surface. So when the entire surface is different, naturally the representative volume element also will be different, isn't it? So this idea of coming out for a generic one is meant for mapping to different bond patterns later on numerically. So we have to take up to that level. Hope I
okay,
have
sir. We may stop here. If the participants have other questions, they may send it to us and we'll send it to you, sir. For later on, we can clarify if they have any.
Yeah,
other...
I have crossed 3 minutes of the committed time. Sorry for that.
No issue, sir. No issue,
Okay.
sir. Thank you,
Thanks
sir. Thank you for
the
your.
patient hearing. Thanks, Professor Sushanta, for giving me this opportunity to interact with you all people. I'm open for receiving questions, and then we can communicate. Thank you.
Yeah, sir. Thank you, sir, for sparing your time. And the session is very informative, as always. I also attended one of your course in January of this year, and it is really informative. And also, I would like to participants, like if you could visit and all those, maybe in the open day or any programs are organized, they can visit the ACRC and they have.
We'll be pleased to.
The top-notch research, yes. Sir, could you please stop sharing, sir, just for a moment?
The controller has removed that. Thank you.
Oh, okay. Sir, just for 1 minute, sir.
Yeah. Maybe we can take photo.
No, sir. Just, sir, we'd like to present you one small token of thanks from our side, sir. Please accept. Please accept, sir.
Thank you. Accepted.
Small token of thanks.
Nice.
Okay, sir.
Yeah.
Thank you, sir. We'll be in touch.
Thank you.
Yeah. Good night, sir.
Good night.